check meeting is on is recording. Okay, so welcome to the final session. Right, so this will be a session, but there is also the one extra session which I will do a brief recap of what we have discussed so far. So it's not like, yeah, if you want I can in this lecture itself I will give you characterization techniques. How do we actually do characterization in the nanomaterials? Right, so yeah, that thing will be done here. And apart from that, we will just have a brief recap of what we discussed. Right, so the optical and acoustic properties of the nanomaterials. So beginning with that, and also we will have some like special cases of the. We will discuss few applications of nanomaterials, and then we do the CNT part, right? So that's what sir has discussed. So apart from that, I will add the characterization techniques also. And yeah, I'm not going deep into the characterization techniques, but I will just give a brief introduction on how to know whether you found a nanoparticle or not. Okay. So then let's begin our final conventional session. Right. So extra session will be unconventional, this is just a revision, okay, of all these sessions. So yeah. Moving on to the acoustic properties of nanomaterials. Now we have discussed optical properties. In optical properties, we discussed why the metals will not transmit, why the metals do not act as a glass, or why metals are not transparent, and why some semiconductors are transparent, some are not. So, and also we discussed what is the fluorescence, phosphorescence, and chemofluorescence. So different types of these things we have. It just depends upon delay. With increasing delay, you will have different things. Okay. So now coming to optical and acoustic properties, right? So we'll just have a brief recap and then we'll discuss acoustic properties, right? So acoustic properties of nanomaterials. Now, again, we know the shape influence the shape, like whether it is 0D, 1D, 2D, right? These will influence or proportional to SPR, and we all know, I have explained many times, SPR is a surface plasmon resonance. So now coming to the 2D shapes, okay? Let's take 2D systems. Now they exhibit, see, they exhibit both longitudinal and transverse plasmons. Right. So what do you mean 2D? 2D are nothing but the nanosheets. Now you can have the longitudinal one also, or you can have a transverse one also. Right. So for example, if I say this is my axis, this is my longitude, and my surface transverse will be like this. Okay. This is in the plane. So let's say this is the XY plane, but this is not XY plane, this is YZ plane. Right. So now again also we know, for example, if I take 2D materials, they both have longitudinal and transverse plasmons. And when I'm talking about one-dimensional nanomaterials, let's say if I'm talking about 1D systems, Now, what do they show? They only show longitudinal modes. Or you can call it as a nodes also. So it's only, so for example, if I take, this is my any nano rod, then my plasmons will be like this along the axis. Okay, so and longitudinal nodes along the axis and traverse ones along the diameter. So this. So these transverse ones are not that effective when compared to the longitudinal one. Now, what about the 0D? The 0D systems. So, example, simple spherical nanoparticles. Now, they can, these, for 0D dimension, you can actually tailor or change depending upon the core shell structure. What do we mean core shell structure, right? So core shell structure is nothing but you have a circular nanoparticle and it is a hollow one, and in that you will have another one. If I see the cross section, here is the gap, and that's why we call it as a core shell structure. Now, so what actually happens? So thinner the metallic shells, like these will be a few layers if you take, right? There will be few layers of thickness. Now thinner these metallic shells, there will be more redshifts, means towards the longer wavelength, because the plasmon frequency will decrease. Now again, what does the plasmon frequency depends on? The plasmon frequency depends on the thickness. Right, if you have very thin sheet, then you will have very longer wavelengths. If you have simple, right, for example, let's say if I have a surface, now some light falls on it, then my electron cloud will start oscillating. The electron cloud will start oscillating. If you have more number of electrons, let's say if my material is large and you have more number of electrons, then my wavelength will be a shorter one when compared to this guy. Now again, not only this, so for example, if I have two agglomerated nanoparticles, right, so this is my agglomeration happening, then even for agglomeration, because of this agglomeration, there is this, what do you call it, resonance frequency, because you have plasmon here and there is another plasmon here, and if this frequency doesn't match, then what happens? Then you will have destructive interference, and because of that, again, lower wavelengths. Right, so that is again one thing. So thinner metallic shells induce redshifts, so this thing I have explained, towards longer wavelengths, so because the plasmon frequency decreases. And then you have the surrounding medium also will affect. So for example, this is my nanoparticle. See, if my refractive index, or let's suppose it is in a certain medium, let's say this is my medium, and so let's say, let me draw it properly in different colors so you can understand. Let's say this is my nanoparticle. Okay. Now let me explain this more clearly, right? So that people can understand why the thinner nanoparticles will have redshift, because see, logically when you think it, lesser the number of electrons, easier, the more energy they can absorb, and the more energy they can absorb, and then you have more oscillations. That means the wavelength should decrease. But here the thing that happening is opposite. So let's take the metallic nanoparticles. Let me tell you the reason behind it, because there is a very interesting effect. Okay? So in metallic nanoparticles, and we also SPR, and you can also call it LSPR, or localized surface plasmon resonance, which corresponds to the collective oscillation of conduction electrons against the restoring force of positive ions when excited by the light. So for example, these are my charges, and you have this electron cloud. Instead of using this, I'll use this guy. Okay. So let me use blue color. See, even though this is not a good resemblance, but let's assume these are my positive charges, or you can call it as the nucleus. Positive charge is the nucleus, and this is the blue. The blue thing is my electron cloud. So you cannot pinpoint the electron, right? Because it has a wave particle duality. So we say that it is a more or less an electron cloud. Now, again, what is LSPR? LSPR is a collective oscillation. So the collective oscillation of this electron cloud, collective oscillation of electron cloud, against what? Against my positive charge. Positive charge, or positive ions, I can call it positive ions pull. So when this happens, when excited by light. Okay, so when they are excited by light, you will have your oscillations. Now, what is the plasmon frequency? How do you write the plasmon frequency? Now let's take how this depends. Let's take a proportionality itself. Let's have an empirical relation. Let's not derive this thing, because it will take a lot of time. So now one thing we know, the frequency will depend upon charge. Okay, and we do not know whether it is a square, triple, or let's just put it like this simply. Let's say this electron charge, and let's say it is a power of n, because the frequency will depend upon charge square. Mostly if you derive the Bohr model also, you will have charge square, and then you will have the effective mass. Effective mass, why? Because I have these two guys, right? So you will have effective mass. Right, it is directly, this is straightforward. You larger the mass, you have less frequency happening. So and then you have, and because we are talking about medium, so let's take permittivity of free space. And one thing we are missing, that is the conduction electron density. And please remember, only the conduction electrons will participate in localized surface performance. Conduction electrons. Conduction electrons means which are lying in the conduction band. So these guys are important. Now again, just not the conduction band, it's the density. So N will be density of these guys. Okay, so N is my small n is my density of the conduction electrons. Now again, I will explain again. The plasmon frequency will depend upon charge. Again, n will be square, because it is mostly the square, times what is my density of electrons in conduction band, or conduction electron density, divided by effective mass into permittivity of this space. But in nanoparticles, this bulk value is modified, right? Because the conduction band is not a band itself in nanoparticles, because it will get dispersed, right? And also there is a particle geometry. So, but in nanoparticles, this bulk value will be modified, and you have the first thing coming is the particle geometry. So, what are the particle geometry? Curvature, shell thickness, which I have explained before. Shell thickness will come into picture, and then you have surrounding dielectric, and then you have coupling between inner and outer surface. So this thing will define, right? So this will define what is the frequency. Now particle geometry, we will come to the particle geometry because we are considering the shell thickness, right? Now what happens in core shell nanoparticle? Let's consider a metallic shell surrounding a dielectric. Okay, so SiO2, let's take silica core or gold shell. Let's take silica core. This is my silica, and this is my gold. So you have gold shell, inside that you have silica core. Okay, now the structure, this supports two coupled plasmon nodes, because each one will have definite surface plasmon elements, right? So SiO2 will have its own SPR, and gold shell will have its own SPR. I will write again. This is SiO2, and this is, in this shell you have gold. Okay, this guy will have its own SPR, and this guy will have its own SPR. Now let's say SPR1 and SPR2. Now these two will couple. SPR1 plus SPR2. Now first one, the outer surface. Let's talk about the outer surface more. Now electrons will start oscillating here, oscillate the outer metal dielectric interface. So this is my, let's say this is my 8th, so they will start oscillating here. Now the next thing is electron oscillate at the inner metal and core interface, so they will oscillate here, here also. Let's say this hole is supported by a core. Okay. Now I will write it again. So this is my silica, this is my gold. Okay, so this is my gold, this is my silica. So this will, you will have SPR1 here, which is between gold and air. Air is our dielectric, right? So let's not take any other medium, just take air. And then you have silica. You will again have SPR2 here. SPR2 is between what? Silica and gold. Now these two will interact. And how do they interact? So we heard this hybridization theory, right? For example, if you have S block, S orbitals and P orbitals, they will hybridize and give you sp3 orbitals, like 1s and 3p orbitals. 1s and 3p orbitals will interact and form the hybridization, which will give you 4 sp3 orbitals. It's nothing but the degenerate values. Degenerate values are nothing but, the degeneracy is nothing but the same energy values. Okay, so that's the thing. Now again, so these two modes will undergo hybridization, giving two hybridized plasmon frequencies. Okay, one is my bonding, which is symmetric mode. That means lower energy, because once you form a bond, you have low energy state. When you have a low energy state, if you do the oscillation, and because the energy state is low, so you won't have any higher energy, and even if you excite that, you will have less energy, right? So that's why you will have redshift. And the next thing is anti-bonding mode. Anti-bonding or anti-symmetric. See, these things we have seen, right? Bonding, molecular orbital theory. One you have bonding and anti-bonding. You have studied in plus 12, right? So whenever we're talking about oxygen, when two oxygen atoms comes close together and they form a bonding and anti-bonding molecular orbitals, right? This thing we have even drawn like this, right? So you have P here, this will be anti-bonding, this will be bonding, right? So I hope you can recall this. Yeah, so anti-bonding, anti-symmetric mode. And because the anti-bonding, anti-symmetric mode, this lies above this guy. So the energy levels will look like this. See? Let's say your orbitals. This is from oxygen, right? First atom, this is from oxygen. Second atom. I'm just taking example, okay? So this is my anti-bonding. This is my bonding. Right, and when you see the energy levels, this guy is lying at E2, this is E1. So E2 will be greater than E1. That means it has higher energy, and you excite with your photons, then this will have even higher energy. So that's why you will have blue shift here. Now you know, right, how the red shift and blue shift happens in surface plasma resonance. Now the next part is how the thinning of shells, giving me red shift. See, as the metal shell gets thinner, so the inner and outer surface plasmons couple more strongly. Why? Because the electron oscillations on both sides feel each other more easily through the thin metallic layer. See, if this is my shell, okay, this is my shell. So this guy will oscillate with dielectric, this guy will oscillate with some other thing. Now when I decrease the thickness of the shell, so this will have separate frequency, this will have separate frequency. Now if I decrease the thickness, let's say I have made very thin. When you do this, these guys and these guys will have same type of frequency. That means we are going towards the bonding side. And when we are going towards the bonding side, then what does that mean? So when I made very thin, these two will get strongly coupled. See, I am explaining in a more physical way because I have to draw so many equations, which I am not doing it because it is very like time taking and also out of the scope of this lecture. So I am just physically explaining it. So please keep with me. Yeah, so SPR1, you have SPR1 and you have SPR2. The same goes for SPR1 and SPR2. And because they are so far apart, they cannot feel each other, that means the frequency will be different. And when you decrease the size, the thickness of the shell, then what happens? The thickness of the shell, then these two will have almost same frequency and they will strongly couple. And whenever they strongly coupled, you will have bonding we are moving towards the bonding stage, this the symmetric mode. And when you have a symmetric mode, the energy is low, and your energy is low, your lambda is large. That means we are going towards redshift. That's it. So strong coupling enhances the bonding mode, so lowering its energy. That is one point. And the effective restoring force for electron oscillation decreases. So in a thin shell, fewer conduction electrons are available to restore displacement, right? So also more field extends into dielectric field, which has a higher permittivity than vacuum. So this thing is not, this is more towards the dielectric of the air. So let's not talk about this because it is not very, I mean this is also dominant, but more dominant is this guy. Let's say this guy is 70% dominant and that guy is 30% dominant. So it's more like your dielectric value will move towards the dielectric core will move towards your dielectric constant of your air, so that's why the frequency will decrease. And to explain this, there is also this Me theory. You can refer it if you have, if people have interest. So resonance square will be equals to frequency of particle square, so L divided by 2L plus 1, and this is a screening, okay, so L so sigma m is effective dielectric constant, both the core and shell. So yeah, that's it. So this guy is one relation, and the more physical intuition, right? So simplified analogy will be when the shell is thick, the two oscillate independently because they are very far apart. They will oscillate independently. When it is thin, it's like a spring, right? So which couples them, so they will move towards the bonding side, and you will have your redshift. So that's all about how my thickness will change my SPR. Okay, so we have used a lot of time in explaining SPR, right? Now where did we use this SPRs? These are used in light absorption emission applications like optical sensors and chemical labels, photothermal therapy, and calorimetry detection systems. Now coming to the acoustic properties at the nanoscale, see, the acoustic properties are less significant. This is completed, right? So coming to the acoustic properties. Now these are less significant at nanoscale are because the wavelength of sound, right? So wavelength of sound lies from microns to kilometers, which is much larger than 100 nanometers, right? So the wavelength of sound lies between microns to kilometers, and our size of nanoparticle will be, or nanomaterial is less than 100 nanometers. So we know 1 micron will be equals to 10 to the power of 3 nanometers. So it is 1000 times larger, so it's not that much effective. But you find this, there is no strong interaction between nanomaterials and acoustic. But however, we have seen the ultrasound is often used in nanomaterial synthesis, sonochemical methods. This we have discussed. So this is the only thing you will find in the acoustic, how the acoustic is used in nanomaterials. Right? And see, and also the nanomaterials can indirectly affect acoustic propagation in bulk media such as seismic materials, So that's all about acoustic properties, right? There is no big discussion on them. Okay. Now moving on to the special cases. CNTs, which are nothing but carbon nanotubes. Depending upon their geometry, or you can say physical interpretation, you can define in two ways. One is single walled CNTs, and we have multi-walled CNTs. Single wall CNTs, multi-wall, depending upon the walls, how many walls are there, right? So again, it is like a core structure. So if I draw so you have two CNTs here, CNT1, CNT2. So that's why we got as a multi-walled carbon nanotube. Okay, and there is also another based on the sheet rolling, based on the geometry, how the hexagons are arranged. You have one is the armchair, and then you have a zigzag one, and another is the chiral. These three are based upon how the hexagons and pentagons are arranged. Hexagons are arranged. Okay. Now, so coming to CNTs, and the guy who invented is Sumio. And how did he invent it? It was by accident, because he was examining the electric arc between two carbon electrodes. So while examining the suit, he discovered these CNTs, and also because of this, the fullerenes, Proto and Smiley also discovered these fullerenes or buckyballs, which is a C60 molecule. Okay. People call them buckyballs. That was just a okay. But actually we call it as fullerenes. Now, in CNTs, the carbon molecules will self-assemble in a cylindrical fashion, and in buckyballs or C60, the carbon molecules will self-assemble in like a soccer ball, more or less. Now, how do the CNTs? These are my CNTs, not CNTs, and this is my buckyball, C60, and these are how they look like. Okay. Now moving on to CNTs. So what exactly are these CNTs? CNTs are cylindrical molecules with diameter ranging from, again, CNT is one-dimensional nanomaterial. That means one dimension, not in nanoscale. Okay. So if I take tube, then my x and y are less than 1 nanometer. or sorry, not 1 nanometer, less than not 1 nanometer. It lies between 1 nanometer and few nanometers. So it lies between 1 nanometer few nanometers. But Z is more than 100 nanometers. Okay. So length may even reach up to few microns. Okay, so that long. And now how do they look like? They look like a graphene sheet being rolled. Graphene sheet being rolled. So you know, right, when you roll a sheet, it will look like a cylinder. Right. So when you roll a paper, actually, when you roll a paper along any axis, you can roll along this axis, you can roll along this axis. It will, the changing thing will be its diameter and the height, but it will look like a cylinder. Right. Now, again, depending upon see this single wall and multi wall, or the metallic or non-metallic, will depending upon the processing conditions. Right. So depending upon processing conditions, the CNTs can be either single wall or multi wall. Now again, there are different types of single wall nanotubes. For example, carbon nanotubes. You can have metallic, semiconductor. Right. And see, I have mentioned before, depending upon the shape of the position of hexagons, these three are made. Now how they are made? Let's say, do I have? Yeah, I do have this. This is my graphene sheet. What is this guy? So this guy is my graphene sheet. And in graphene sheet you can see we have hexagon, a good hexagon, or a humble in more scientific way, or more physiological way. You can call a humble 6-membered carbon ring. So with one electron being delocalized, right? So see, the carbon should satisfy 4 bonds, which happens in diamond. But here the carbon is only, see, wherever you see, the carbon is only matching with only 3 guys. That means one electron is being delocalized. So that electron will just travel from here to here, here to here. So it just happens randomly. Okay. Now, so graphene sheet, just as I have said before, depending upon the rotation of this paper. So let's say this is my graphene sheet, and I have taken the graphene sheet. Now I am trying to wrap it. So I am trying to wrap it along this axis. Okay. So if I try to trying to wrap it along this direction. Okay, so this guy will be touching this guy, or I can take, okay, we'll just take it like this because the arrow is there itself, right? So this guy will touch this guy, right? So how, okay, before that let's people even gave a mathematical relation. Okay, so let's say this is my x and y axis. Okay, things. So let me draw. Let me draw the atoms itself because the space is very congested to explain there. Okay, so the next guy will come. Do I have 6? 1, 2, 3, 4, 5, 6, 6. Okay. This is 1, this is 2, this is 3, this is 4, 5, 6, 1, 2, 3, 4, 6, 1, 2, 3, 4, 5, 6. Okay, so let's draw them. And then you have another one here coming. I hope I'm not wrong because I feel like I'm making a mistake. See, so this is my hexagon. The next hexagon comes. Okay, instead of drawing like that, we will use this. Let's first draw the hexagon itself to avoid the confusion. Okay. Now the next guy will come like this. Okay, okay. Now I got it. Please bear with me, my drawing skills are not that much exceptional. So let me draw one more so that I can write my axis clearly. Okay, this is good enough. Now, the first thing is you have the vectors. Let's take the vectors. Okay, the first vector that is coming. So the first vector that will be taken as B. This is my B vector, and this guy, let's say. Okay, instead of that, I can take it, no problem. So I can take this guy as A, okay, or I can take here. See, the vector, you have B vector, and then you have A vector, right? So again, these two vectors are of same magnitude because they are just bond length, and bond length is same, edge length of a hexagon, so it will be same throughout the material. Now what is my C vector? The resultant one. Right? And because we have given the unit vectors, we can write any vector in terms of these two unit vectors, which is MA plus MP. Okay. Now the first thing is, let's move on to here. Now if I join this guy and this guy, right? So that will be called as, so that guy will look like this. So yeah, so that guy, if I join them, at first I will have an armchair, and then I will have a zigzag. So if I join this guy to this guy, then I will have what do you call that? Armchair, right? So, and if I join this guy to this guy, okay, then I will have zigzag. And if my vector, if I join any of these guys, okay, maybe I will join this guy, or I might join this guy or this guy, then it will be a chiral. This guy, and this guy. Then it is a chiral. Okay. So one is my armchair one, the zigzag one, and in between I have chiral one. Now let's denote in terms of vectors. Okay. So here A and B are my unit vectors. So A and B are my unit vectors, and N and M. So N and M are dimensionless. With values signifying the magnitude. Right. So now coming to different types. So the magnitude of chiral vector C is the circumference of an nanotube. So now any vector C is my circumference of C and T. That's it, right? Because this C vector is just so because we are rotating about the axis, right? So this is my A. Now this is A, this is B, and my C vector will be here to here. It's just a circumference of my C and T, right? So if my C is just, if I'm rotating them, like touching this guy to this guy, this is my C, and I'm touching my first atom to the second atom, and that I'm what do you call it? So I'm coiling my C and T around these two guys, then this will be my circumference. And because see, this guy, let's say this is the atom 1, and this guy is atom 2, and my C is this. It's just a circumference. Now, and its direction related to the unit vector A is the chiral angle. So what is its direction with respect to A is my chiral angle. Now again, the magnitude of C will be directly your circumference. Circumference of a cylinder is 2 pi r. So C equals to 2 pi r. Magnitude. Now these parameters will tell you how the graphite sheet is being rotated. And we have seen three types. So let me write three types. So first one is armchair, let's say, and how armchair nanotube will look like. So armchair CNT, how the armchair CNT will form. See, you have seen, oh, I made a mistake. This guy is zigzag. This guy is armchair. See, you can get confused with the names when you are directly saying, but when you derive it mathematically, you will just tell which one is which, right? So the best way of remembering things is either you have an equation or you have any physical theory, so that you can just directly correlate them and you can say, yeah, this guy is that and that guy is this. And how could I remember? Because from the mathematical equation, whenever there is m equals to n, m equals to n means, so a vector n times a plus m times b. Here n and m are equal, that means m equals to just an a plus b. Right, and this type happens in armchair. Because is a resultant, right? So A, B, your C will do it. It's in perfect proportions, 45, 55. And it will look like an armchair, right? Like this. Find everything. Like this. Now, the next one is the zigzag one. Now, how does my zigzag one look like? What should be my vectors? Right, vector values. So we have defined for armchair. Now zigzag one will have, we have defined, what was our axis actually? So my A and B, right? So let's say, I can take any one as an offset, right? It will not make very much difference. So I can make either m equals to 0. If I take m equals to 0, right, then you will have zigzag one. Okay, it's just only you will have an A. Just C is equals to, that's it. Right, so this guy will look like zigzag, in a zigzag manner. Now the chiral type occurs when the chiral vector number will lie between, will have n and m at different values, and they should be in integer. Okay, they cannot be rational numbers. So n and m should be any integer values, and the chiral angle will be intermediate between 0 and 30 degrees. Among these three different types, armchair as single wall nanotubes are mostly metals. So those with n dot m equals to k, then you will have are semiconductors with a small band gap. And there are other one which, apart from these guys, k should be an integer. So if I have n and m equals to n dot m equals to an integer, then those will have a small those semiconductors will have small band gap, and if it is not, then they will have a bigger band gap, which is inversely proportional to the CNT diameter. And we all know CNTs have very exceptional properties because of their what do you call elastic deformation, right? Mostly. So CNTs exhibit extraordinary properties due to strong covalent bonds, and we all know if carbon atom has, so what is the atomic number of carbon? Carbon is 6, right? So carbon is 6, then my electrons should be 6. So 1s2, 2s2, 2p2, right? So 1s, 2s. Now, and to achieve octant electronic configuration, they should be filled with 4 more. So that's why you need 4 electrons to satisfy octant electronic configuration. Octant electronic configuration, right? OEC. So that's why carbon takes 4 electrons. Now, the carbon will bond among themselves. So, how do they bond? Now, this electron can jump here, and this guy can be written as now here 1 s orbital and 3 p orbitals. That's what happens. 1 s orbital and 3 p orbitals will take. So, it is from oxygen, right? Oxygen, then it should have oxygen. What is the number of oxygen? Oxygen is 6. Anyway, so 1s and 3 orbitals will engage in hybridization, and because these 3 orbitals are 3 different energy states, and they will hybridize and have degenerate. They form the degenerate states. So with equal energies, so we will have 4 sp3 hybrid orbitals. sp3, right? So, but it actually happens in diamond, but not here. See, you have, yeah, again, special types, right? You have single wall and this multi-wall, and these are again, so armchair, zigzag, chiral. So armchair is nothing but your n equals to m, right? And zigzag, you have m equals to 0, and you have an integer value. So this is the kind. Now, moving here, but in graphene you have only sp2 hybridization, but still there are strong covalent bonds. Covalent bonds are stronger, right? We all know that. And their quasi one-dimensional structure, we all know that. And because of this configuration, they have very high what do you call the Young's modulus. They can withstand very large amounts of stresses with very little elastic deformation. So Young's modulus is 1 megapascal. Sorry, 1000 gigapascal. Right. And also you have very large current densities. We all know white has large current densities, right? So large current densities, right? So ranging from 10 to the power of 9 ampere per centimeter square. So it has very large current densities and also very good and exceptional thermal conductivity. So thermal conductivity will be ranging from 6000 watt per millikelvin. And why? Because of that one delocalized electron. Again, localization delocalization is nothing but how freely an electron can move. Okay, how freely it can do the random walk. Delocalization means we are not bounding the electron to that some space. So okay, what happened? One delocalized electron. And because of this guy, they have very high thermal and electrical properties. So what are the different ways to synthesize carbon nanotubes? The most common methods are arc discharge method, because that's how they actually made before. And there is also, you also have a CVD, chemical vapor deposition. So how this chemical vapor deposition? So let's talk about PVD or CVD, okay? PVD and CVD. So we all know the difference between PVD and CVD. In physical vapor deposition, you just use the physical properties and of a material. In chemical vapor deposition, you use the chemical properties. So for example, physical properties are nothing but the melting point, supersaturation, boiling point. These will come into picture. And when I'm talking about chemical vapor deposition, we are talking about the chemical reactions. Right? So how actually happens? You have a boat here, and there is this furnace thing, heating one. And then on it you have substrate, and you can take catalyst also. So what you're trying to do is, now you're trying to pump the carbon atoms. Okay, so for example, you have some carbon molecules, okay, or any carbon bearing material. Now what are you trying to do is, you are trying to evaporate. Let's say this is my carbon bearing material. I'm just showing it, okay? It's not like actual process, what happened, but more or less this is how they do. So you have a carbon bearing material, and when you try to evaporate it, you have carbon molecules or carbon atoms in it. Now this catalyst, what it will do is, or nickel catalyst, it will, any type of catalyst, okay? You can take any catalyst, or you can take nickel catalyst, okay? So the carbon atom will fall onto the surface, okay, because it is very far, and you have very high temperature here, but here the temperature is low, not that much low, okay? So the carbon atoms will fall here, and once they fall on it, because they will condense, they will form, they will start to diffuse into the nickel catalyst. So at a certain temperature, any material have some saturation limit. So this is the amount of carbon atoms it can take. So it cannot take all the carbon atoms, right? So every atom or every material will have some saturation, and whenever you reach that limit, then it will start throwing out whatever extra is coming out. So what happens is, then the carbon atoms will slowly, so carbon atoms are still coming, then the carbon atoms will slowly starts coming out from the catalyst. They will start slowly coming out of the catalyst, and this is how, and in the form of cylindrical tube. The carbon atoms will come out in the form of cylindrical tubes, and this will grow, because the carbon atoms are still coming into catalyst, and this will grow. This is how you will get your CNT. So they are very impure, because you have your catalyst stuck here, right? And sometimes you can even have multi-walled carbon nanotubes, not even single wall, you can even have multi-walled carbon nanotubes. Okay, so making them defect free is a huge challenge. Making them is not a challenge, but making them defect free is a huge challenge. Now, yeah, you have arc discharge method and CVD method. In CVD, you use some gases, okay, to deposit carbon. Now, and these methods have, and they have huge improvement, but still they lack few things. But they still suffer from low yield, again very high cost, difficulty in like making the diameter of a desired diameter or tuning the diameter, you can say it, of CNTs. And the major problem is making a single wall CNTs without impurities. Just I have said before, making single wall and without impurities, that is a major challenge. Now, there are even other methods. Let's say you have laser vaporization. Laser vaporization is more localized vaporization, right? Instead of the whole thing being vaporized, it's more like a local vaporization. And we can get single wall nanotubes from this, and the diameter will be 1 to 2 nanometers because of the local vaporization. So advantage is, again, it has a few defects, good size control, but the main disadvantage is it is very expensive process. Okay. And then again we have arc discharge and CVD, which I have discussed. In arc discharge and CVD, you can both have single wall and multi wall nanotubes. So it is easy to produce, but you have defects and the tunability problem. No. So the main drawback is the large concentration of impurities being embedded inside the CNT network. So the powder needs to be filtered, right, to reduce the amount of impurities present. This is normally achieved by acid oxidation or gas oxidation or filtration. Because, and whenever we try to do, sometime when we do oxidation or dissolution, some amount of CNTs will get dissolved. So to remove the impurities, we do acid digestion or oxidation, you can call it, right? Acid oxidation or digestion, or you can call it as a selective dissolution. What do you mean by selective dissolution? So for example, if you have an acid, okay, and you have A and B mixed. Now what this acid does is, it will either dissolve only A throughout B, that means B will remain as it is, or it will only take A or throw out B. That is called as selective dissolution. So that's what we are doing here also. So whatever in selective dissolution, what we do is, we dissolve our impurities like nickel, and the acid will throw out or remain as it is are CNTs. Even though how careful you are, some part will again get dissolved. And sometimes they even damage CNTs also. So again, these because we have to do many times, right? So we have to make sure we shouldn't increase the concentration too much. And when we decrease the concentration, the amount of dissolution, see, the dissolution will depend upon the concentration. If you have a high concentration of acid, the dissolution will be very fast. If you have a low concentration of acid, the dissolution will be very slow, right? So if you have very high dissolution, everything will get dissolved. That is not required, right? We need low concentration, but only the impurities should get dissolved, and that will take time because we are playing with the concentration, right? So again, that's why they are very time taking and very expensive. But still, they are being prepared. Why? See, these were also used in Titan, right? The Titan submarine. They used different. They used a composite, and in that composite there is they made a cylindrical thin strip of these fibers, nanofibers, carbon fibers. Sorry, right? So they even heard the sounds of carbon fibers being breaking. You can clearly listen to the sound of the fibers being like breaked in the Titan, because the Titan looked like this, right? It's more like a cylindrical shell, and then they have this curved part, and then they have the motors here. So here it was a titanium alloy, because the glass reinforced one, titanium one, and here they have very glass reinforced. So this part was good. There was no problem with this guy. This part was good, but the only problem was with this guy. Why? It was simple, because when you do the cross section, it was made from fibers, carbon fibers, which are being like rotated on this guy like this. And when you apply very large amount of pressure from outside, because you have crushing pressures at the bottom of the sea, right? And you can even see these being broke off. And when they were submerging for like third or fourth time, they did listen these the carbon fibers being break apart. Right? You can clearly hear that sound in that YouTube video also. So yeah, even though they have exceptional strength, but still there are some things that needs to be considered. So, and apart from the structural one, they have very good amount of electrical and thermal properties. So coming to that, in the area of nanoelectronics, so for example, see, you want a very small chip. See, the smaller the chip, the better will be the compaction, better you can store your device or you can move your device. And we have been saying that each NVIDIA graphics chip contains so many number of cores. We have been listening. So NVIDIA call them as CUDA cores, and they even have the tensor cores. Tensor cores are more for ray tracing. The people who game, they can relate what I'm talking about. Tensor cores are used for ray tracing. So ray tracing is nothing but in a game, for example, you have a sunlight, and each ray is being traced, like they are doing calculations. In graphics card, what's the graphics card do? It traces how the ray is going, and for example, if there is a shiny object and if it bounces from here, it again calculates where it is going. So I guess it is more like 4 reflections. So NVIDIA graphics card do the ray tracing until the 4 or 5 reflections. I'm not sure about the number, but yeah, that's the power of the NVIDIA graphics card. And then you have AI tops. AI tops is mostly for AI, the machine learning one. So on which they are mostly focusing on. So in CUDA cores, you have millions of transistors which are acting as a simple calculation. Okay, so yeah, and for that you need very small transistors. So we are slowly reaching that the minimum size for a transistor. Whenever, see, people have this question, right? Why cannot you make a very small chip? Because NVIDIA graphics card comes more or less of 3 to 4 mm, I guess, 5 to 6 mm. I don't know what is the size of the chip, but actual size. So it is more or less like this. Why cannot we make very small transistor? The reason behind is, see that for whenever you talk about transistor, NPN or PNP transistor, so you're talking about you have these walls that dividing them. Okay, so when you make them so small, the electrons, see whenever you apply, okay, so instead of writing this, let's say this is my NPN junction, okay, NPN. Now let's take system here. Okay, so whenever you try to apply potential to this, the electrons will flow. That's what whenever talking about when you act transistor as a switch. So whenever you try to flow electrons, it will, if it is a forward bias, then it will allow the electrons. If it is negative bias, it will not allow the electrons. That's what the transistor, that's what the diode will do. Right, that's what we have been seeing or studying from class 12. So when you make your chip very small, right, so this wall becomes so thin, that the electron may jump from here to here without even supplying the voltage. So that is called as electron tunneling. So in one-dimensional potential well, we only discussed whenever we have infinite potential well, right? We have infinite potential well and here it is zero, which is not the case. This is for just understanding or deriving that part. Okay, this is not always true. So what happens if I have a certain value? What happens if V is constant, some constant value? Then what happens? Then the electron wave function, actually the electron wave function should look like this, right? But it will not look like that. When you have a constant value, you can still find your electron here. Even though the probability is low, the psi square is low, but your electron can still be found here, and that is called as electron tunneling. So that's what happens here. Without applying the potential, the electrons will jump from negative to positive. Right? So to make these things happen, to have much miniaturization motion, people are doing different research on why not make CNTs as an interconnects. See, CNTs are very small. They can be made of 18 nanometers. This is a drain and this is my source. Why cannot these CNTs can be used as interconnects? Right. So these are field effect transistors. Okay. So which can be like electrical signals between transistors are currently made of copper. Instead of using copper, why not we use these things? Now the copper, whenever used as an interconnect, the copper will heat up more. So what about CNT? CNT have much more electrical or thermal conductivity when compared to copper. So they can be cooled fast than copper, right? And also conventional metal wells can typically exhibit current density of 10 to the power of 5 until resistive heating becomes a problem. On the other hand, you know the CNT is the current density is 10 to the power of 9. Right, this is because of the electronic states are confined in the direction perpendicular to the tube axis. So I have explained this before. So yeah, so in CNTs you will have very large electron conduction density along the conduction. It's more like conduction along the z-axis, along its axis, because of the delocalized electron. And we even have heard FET, right? Field effect transistors. MOSFET, JFET, right? So these are transistors used for like where they are used actually. They are used for example, if you have a weak signal, now you want to amplify it. So there we used field effect transistors. So it's more or less like weak signal amplification. And we all know all these semiconductors are made of silicon, transistors are made of silicon. So now if what if we can use CNTs there? CNTs can have less than 1 nanometer diameter. It would allow more of those switches to be part of the switch, right? More amount of switches, more will be the power. More will be the power, the better will be your graphics card running, right? So that is about field effect transistors. Now CNTs are also being used in fuel cells. Okay, so fuel cells and batteries, and also for storage applications. So in case of if you're talking about fuel cells, CNTs have been used for storage of hydrogen, right? Because whenever you take any material like steel or any other thing, if you want to store hydrogen there, you have, because the hydrogen atom is very small. This is my steel shell, let's say, and here I have hydrogen. Now, and because the hydrogen atom is so small, the hydrogen will start diffusing into my steel. And it will give me an effect, the most famous effect, which is called embrittlement. Now what happens in embrittlement? Embrittlement is nothing but the iron will diffuse into the steels. Either it may form metal hydrides, which is FeH2, and what happens if it will form FeH2? FeH2, when it forms, it will increase its volume. So whenever you have increased its volume, you have cracks formation there. And whenever you have a cracks, if you have a pressure, then the crack will propagate. And when crack reaches a certain length, you will have sudden fracture, and when you have a sudden fracture, there will be a blast. That's why. And CNTs can use to store hydrogen. Okay, so yeah. Now again, to store hydrogen, you need cryogenic temperatures. One is cryogenic temperatures, because that is not possible, because again cryogenic temperatures are very hard to maintain for a longer time. And the next is why not make solid cells which can emit hydrogen with some reactions. So that is one way. So that's what we have done. And the other one is our fuel cells, not potential cells. So you can have CNT porous separator, and there you can use them. So yeah, some people are even using graphite sheets also, right, for in these type of applications. Now let's stop with this application. Let's move on to the nano composites, because we only have half an hour left. So nano composites, again, these are like three-dimensional nanomaterials. Now what do I mean three-dimensional nanomaterials? Three-dimensional nanomaterials consists of one part of it being in nano dimension. This is what I mean. Three-dimensional nanomaterials are those nanomaterials in which one part of is in nano dimension. Okay, so in composites are made of two phases, right? So one is matrix, and there is this another phase, reinforcement you can call, and composites may be metal polymer, metal ceramic, ceramic polymer, so they can be of any variation, right? So there are four classes of materials, right? Basically we define one is metal, depending on bonding more or less, metals, and then you have polymers, and then you have ceramics. And the fourth class is composites, but it is more or less a combination of one of the three that we discussed before. Now, so you can have matrix, and inside matrix you have nanomaterials, nanoparticles, or any type. Okay. Now, among the various nanocomposite types, the polymer matrix nanocomposites have been the most trendy. Right, so polymer matrix nanocomposites consists of matrix made from polymer material. However, the second phase, which is more dispersed in a matrix, has a nanoscale dimension. Right? So, again, how do you differentiate the glassy and rubber phases? Right? So, whenever you heat a glassy phase, it will have a glass transition temperature, and then there is a transition region. It's not like sudden conversion from glass to rubber. Okay, so there is this transition region where some part of being continuously being converted from glass to rubber. Okay. So I will not discuss in brief about the nanocomposites, because sir has explained it, and there is no need to go in depth, because not many questions will come from there, and also because of less time, there is sir has explained very little. So let's talk about, let's just have small recap, okay? Let's not go deep. So polymer matrix nanocomposite. So polymer matrix nanocomposite uses polymer matrices. Polymer matrices means, so polymer matrices. What are they? They can be thermoplastics, thermosets, or elastomers. Any of this one can be my matrix, and then my reinforced material is reinforced material, and this can be nanotube or nanoparticles or nanosheets, even plates. Okay. Now, what are the advantages? So, because of this enhancement, there is an enhanced modular strength, because it is a synergistic effect, right? So, we have good modulus, enhanced strength, wear resistance, transparency, and conductivity. Again, lower filling loadings required compared to conventional composites due to the high surface area to volume ratio of nanofillers. Okay, and zero-dimensional nanoparticle reinforcements. Let's talk about zero-dimensional nanoparticle reinforcements. What are the examples? Examples are alumina, silica, calcium carbonate, zinc oxide nanoparticles. Okay, and what are the advantages? You will have strong interfacial bonding. For example, if I take PMMA plus calcium carbonate, if I combine these two, this guy is a matrix, this guy is a reinforced material. Okay. Then you will have higher modulus and higher TG. Whenever you have, for example, if I take aluminum oxide instead of calcium carbonate, then your modulus will get reduced because there is no strong interfacial bonding. Okay, and then you have electrical effects, right? And there is an optical effects because the transparency depends upon small particle size and refractive index. Right. Now coming to one-dimensional reinforcements. One-dimensional reinforcements. Examples, CMPs. Now for this you need a good distribution, or you can say it as for better properties, for better synergistic properties, you need uniform dispersion and then good alignment. So for example, if this is my material, it should have uniform distribution with good alignment and also strong interfacial bonding. So for dispersion, what do? You do the sonication. Sonication breaks CNT bundles into solvents, and shear mixing, which is good for flexible polymers. We can even do chemical functionalization also, adding reactive groups like COOH. Okay. Now for alignment, we do the extrusion, which is the best one. Even for the grain alignment, also we do the extrusion and drawing. Okay. And for interfacial bonding, which involves mechanical interlocking and chemical linkages, and entanglement of polymer chains. Around CMTs. Now that is all about 2D reinforcements. Let's go with 1D reinforcements. Let's talk about 2D reinforcements. Example are layered silicates. So most common is meticlays and mica. They are more or less like sandwich structures. Okay, it's more like sandwich structures, and there are many ways they can be made. One is a solvent-based intercalation, and it also has melt bending and in situ polymerization. So yeah, again, doing this will have a synergistic effect, and the main property will be the modulus. So there will be large modulus because of this two different types of materials. Now coming to the metal matrix nanocomponents, you can even have this guy also, metal matrix nano components. So reinforcements will be, reinforced materials is borides, carbides, nitrides, oxides, and CNTs. And how do you do processing? Processing is best will be the powder metallurgy or mechanical alloy. The best example is aluminum titanium carbide nanocomposite. which tell you have the good uniform dispersion and high strength across wide temperature ranges. So, and even examples are like silver, tin oxide. You can even have Nd2 Fe14b, rare magnets, right? So that's all about metal matrix nanocomposites. You can even have ceramic matrix nanocomposite. Okay. So examples are alumina and zirconia. Alumina or zirconia, sorry. Alumina or zirconia matrix with silicon carbide nanoparticles. See, this combination will have 50% increase in your toughness. So there's a huge jump from this guy when you add this guy. Okay. So that's all about the composites. You can even have this nanocomposite thin films and coatings. That is again the different thing. Okay. So there is also this bio-inorganic nanocomposites. See, what you do is we, for example, let's talk about. You know what? Let's just talk about everything. We still have time, right? So let's talk about nanocomposite thin films and coatings. So they exist as either single layer or multi-layer structures. Okay, so let's talk about multi-layer films. So there is no physical explanation, right? It's just about the materials. Okay, so that's why I'm rushing it, because all these examples are not discussed, right? So that's why I'm, instead of explaining, there is no theory, right? Because we have discussed the different types of properties. Now all we have to do is what are the different types of classes of these materials. So that's why I'm not explaining anything, just I'm giving the examples of these materials. And also what are the advantages. So in multi-layer films you have alternating nanoscale layers. Okay, nanoscale layers. You have titanium carbide, titanium nitride, chromium nitride, titanium aluminum nitride, or alumina layer. Now, either you can take one of these two and you have alternate layers. Okay, you can have titanium carbide, titanium nitride, then you have titanium carbide, then titanium. It's just a sandwich. So what are the advantages? Advantages are high hardness. So interface will resist our dislocation motion just like grains, and because we have so many interfaces, so that's why we have very high hardness and enhanced toughness. Why? Because crack deflection, enhanced toughness because crack deflection at interfaces. And then you have good thermostability. Here's another thing. Okay. And the layer thickness is critical. If we have too thin, then there will be strain relaxation, which results in lower hardness. So also these can be also used for magnetic storage. Okay, so magnetic storage. magnetic storage. So, and then if you are talking about single layer, right? So we missed single layer nano composites. And when I'm talking about single layer nano composites, that means I'm talking about hard nanoparticles dispersed in amorphous matrices. Right. So hard nanoparticles are amorphous matrices. So example is titanium nitride in silicon nitride. They can reach hardness up to like 50 to 60 gigapascals. Okay. So carbon nanoparticle, again there is another class of materials. The carbon nanoparticle coatings in amorphous carbon provide low friction corrosion resistance, useful for aerospace. Okay, and also the cutting tool coatings. So whenever you have, see, we do not use, for example, if you take the chain, not the chain, or you can say the cycle, chain teeth, the rim teeth, right? Rim. So it will look like this. Cycle. It's not sunflower, there's a chain cycles one. Right? So this whole material is not hard, only the surface is hard. So what do? We do is carburizing. Carburizing is nothing but you have a material, you deposit a very thin layer of carbon, and this carbon will start diffusing, and it will form a layer of carbides, and this act is very tough, which has very high hardness. Okay, so this is often done in carbides like tungsten carbide, titanium carbide, on cobalt or nickel matrices. Okay. So now moving to the final one, which is bio inorganic nanocomponents. So what we do is here we integrate biological molecules such as proteins, DNA, lipids with inorganic nanostructures like zeolites. So for example, so we integrate biological samples or biological molecules. So example are proteins, DNA, lipids with inorganic nanostructures. So zeolites, oxides, clay, and CDS, cadmium sulfide. So these are the things, and the interactions are between proteins and DNA offer diverse chemical groups. We know that. So they have acidic groups, basic groups, hydrophilic and hydrophobic groups. So which enables our hydrogen bonding. So we even have amine groups also, right? And which also results in electrostatic interactions and self-assembly with inorganic surfaces. So these hybrids will enable the biomineralization, bioceramics and biofunctional materials with controlled nanostructure and properties. So the key things which include in this bioinorganic composites are self-organizing molecules, templated growth and molecular recognition. So these can be used in biosensors, tissue scaffolds and molecular electronics. So that's all about the bioinorganic nanocomposites. You don't have to dwell deep into it because, again, if you have very, what do you say, if you're until or unless you are working on these things, so you don't have to study deep. See, so that's all about the final session, the final conventional session. We will have an extra session. You will get a mail for that. So please join on that day. On that day we will only do the revision. Okay. So we will not discuss anything new. Okay. Maybe we will try to have some characterization techniques. That might help. We will only discuss small things like XRD. What do you expect when you do XRD of nanomaterials and nanoparticles, and then we will discuss a small part of UVVs, and then we will see in SCM and TM, and then we will conclude this NPTEL course. Okay. So thank you for attending to this session. All the best for your exam. If you have any doubts, you can stay, or you can let me stop the meeting before actually.